Weather forecasting has gotten much better over this past decade, especially for severe weather monitoring and prediction. However, there is still much room for improvement. In 2012, Hurricane Sandy moved ashore on October 29th near Brigantine, New Jersey, resulted in devastating damage in New Jersey and New York, with destructive high winds that toppled houses, caused crane collapse, and even damaged the vertical stabilizer of Space Shuttle Enterprise. The storm surge flooded subway stations, tunnels, and destroyed many shoreside piers. The weather channels have been warning about Hurricane Sandy since it formed, long before hitting New Jersey. But it wasn't until 3 days before the landing that weather prediction models showed so. In fact, 4 days before the landing, most models still predicted the hurricane to move east and not severely impact the states. How can we improve the accuracy of weather prediction? Well, weather forecasts provide an estimate of conditions we expect to experience in the near future, rain or shine, based on current weather conditions as well as statistical models, with some physics and guesses. The environment where weather happens, the atmosphere, is highly turbulent. You must have heard the term turbulence. But what does it mean when we say the atmosphere is turbulent? You can imagine the atmosphere is composed of eddies of many different sizes. Each eddy is like swirl motion of velocity, temperature, humidity, or even dust particles. For example, this is a picture of the Kilauea volcano in Hawaii 3 weeks after its explosive eruption in 2008. The plume rises from the ocean has eddies of distinct sizes. Large eddies that dominate the shape of the plume, medium eddies that add to the shapes, and small eddies that describe the detailed features. You can see the same phenomenon when pouring milk into coffee. Without additional energy input, the larger eddies will break down into smaller eddies and eventually dissipate into heat and disappear. In the atmosphere, the ratio of the size of the largest to the smallest eddies is proportional to what's called Reynolds number, which roughly describes how turbulent the flow can be. Reynolds numbers in the atmosphere are generally very large, which means the small scale is very small, usually on the order of 1 millimeter or less. Small doesn't mean it's not important. In fact, it is small scale that dissipates into heat, which is one of the largest contributors to our weather system. In order to measure the small scale eddies, sensors should be on the comparable size in order to measure the signal. If the eddy is too small, signals will get averaged out and cannot be measured, and we lose information of the very important small-scale eddies. Remember we mentioned that the weather forecast models involve some kind of guessing? Scientists make educated guesses to create models and corrections that have good agreements with experimental data. But if the provided experimental data is biased, models created based on that data will be biased as well, which makes them less accurate. Another component of weather prediction is knowing the current weather conditions. You may have seen weather stations around us that constantly measure wind speed, temperature, and humidity. Because the equipment in those units is quite expensive, we cannot afford deploying more units to collect data, even though that will provide us with more accurate information. Therefore, ideally we want a technology that is both accurate to measure the small scales in the atmosphere, as well as economical for distributed sensing to provide us weather data with improved resolution. With the booming of MEMS technology in the past 2 decades, MEMS sensors have become a part of our daily lives, even though we may not have noticed. The MEMS accelerometer in smartphones automatically rotates the screen when you hold your phone horizontally. MEMS crash sensors are now in every car that trigger airbag deployment when collision happens. MEMS print heads transform inkjet printers from slow black and white printing devices to fast, flexible photo quality image printing machines. In our lab, we design micro and nanoscale sensors to measure turbulent flow with high accuracy, especially in the small scales. We start with a clean silicon wafer, deposit layers of materials to form the shape of designs, including the nanoscale sensing ribbon in platinum. Then, using highly energetic etcher gas to selectively remove the unwanted portion of the sensors. The active sensing element is a freestanding platinum ribbon of which the length is shorter than the diameter of human hair, and its thickness is only 1/1000th of that. When placing these sensors in flow, we can measure scales that are 10 times smaller than what a conventional sensor can do, greatly improve the resolution and captures more information. And since these sensors are very small, we can manufacture about 200 of them at the same time from a wafer the size of your palm, making them very affordable. These new nanoscale MEMS sensors allow us to poke into the small-scale eddies and understand how they interact with each other. The understanding can bring insights such as how to reduce drag to save energy, or promote better weather models so we can be more prepared for what's coming.